Here we are. So let's start out with drawing a free body diagram. Free body diagram, FBD. So it's going to be, it's going to be probably tension, right? TAB. And then we're going to have, interesting. FBC. What is one solid object? Interestingly enough. We're going to have FCD. So one object is causing a few forces. That doesn't quite make sense to me. But I guess I can't split forces up. Interesting. Yeah, no, you can't do that. Okay, I was being very, very foolish. So this is just an object. It goes down, down a bit, and then over. Down a bit and over. Oh my gosh, hold on. There, that's fine enough. And on it is applied some forces. So we're going to have force P. And of course, this is point D. But that almost looks like it's force D, so I'm just going to do that. Point D. It's going to be point C, and on this is going to be CY, CX. Yes. And then right here is going to be point B. All right. So first thing is first, what I would do is I would take a moment about C. This would give us TAB and P, because we know that P is equal to 500 newtons. So really it would just give us TAB. So the sum of the moments about point C are going to be, let's see, this is going clockwise. This one's counterclockwise. So let's start with TAB. It's going to be R. So TAB, how far away is that? Well, interestingly, TAB is both this way and this way. It's both this way and this way from our point C. So how far is that distance? Then we take, so if I was to draw this, it's this and then this. So is this the distance here that we're taking? The hypotenuse? Are we taking the adjacent, or the opposite? Which of these is our R? Because it's going to be an R cross F, which is TAB. That's our force, minus P, which clearly is going to be 300. It's minus 300 millimeters. We say times 10 to the third to the negative third. One of the two. Or we can leave it in millimeters. What they do for the forces, though? These in newtons. So yeah, times 10 to the third. Why not? Times P, which we know is 500. So which of these do we take? Well, the opposite, this is equal to 75. And the adjacent, well, that's 125. So if we square both of these and then we add them, this will give us our H. But is that the R that we're taking? Do we want to know that R? Is that the distance? Well, what causes more of a bending moment? If we had a lever, and I was trying to go down, push down with force downwards on a bolt, I would want this to be perpendicular to where the bolt is. If I was to raise this at any height, it wouldn't do anything. I don't think that would matter at all. So where's our force? Here's our force here. So this height here wouldn't matter at all if we're finding the force. If this is the force applied, C, Y. Cy is a reactionary force. This is our actual force. This is the bolt. So this distance then is the only difference that matters. Let's see. This is the bolt. No, it'd still be this distance. But the force is this way. So then this upper bound right here, this is the lever arm. So it's going to be 125. Okay, so that means that these equal each other, and then if we divide this by 125 times 10 to the third, then that will give us TAB. So TAB is equal to, so let's see, since they're both times 10 to the third, but 500 isn't, so I'm just going to keep it 300 times 10 to the third times 500 over 125 times 10 to the third, which is 1200 newtons. That kind of makes sense. I could see it. It doesn't seem very far off. We have a 500 newton, 1200 newtons. It doesn't seem that far off. It's far off. So now we have TAB. Well, what's that give us? Well, we're asked to find the shearing stress. Shearing stress is like this thing, right? So if I look in my notes real quick and pull up a formula, shearing stress is equal to V over A for single shear. Now if we look here, right, we have this here and this here fighting against this, right? So we have one thing fighting against two things, okay? This would be double shear. So then what's double shear? Single shear V over A, V over 2A. Because A should be uppercase. And well, what's the V? V is the internal force. Okay. So, how do we find the internal force? That's something I'll need to know. So we have TAB. We have all the forces. We need to find CX. So if we take the sum of the forces in the x direction, you'll notice CX and TAB are the only two forces. So TAB is equal to CX, which means that CX equals 1200 newtons. And of course, if we take the sum of the forces in the y direction, then CY also has only one other thing, is going to equal P. So CY is equal to 500 newtons. So now, well, what can we find? How do we find C? CR is going to be equal to the square root of 1200 squared plus 500 squared. And this will give us the reaction force, the overall reaction force. which is equal to 1,300. Okay. So with this, we have our forces at C, forces acting at C. I'm going to try to use that for V. 1,300 divided by 2 times, well, what's our area? Cross-sectional area. We're not given. It's going to be 5. Area 5. Area. Come on, man, area. We only know the thickness. Let me look at my notes again. I take it back. We're given, I found it. We're given the diameter. So the diameter is 6, so it's going to be area. It's going to equal pi times r squared. The r is going to be 3 because the diameter is 6 and r is half of the diameter. So it's going to be times pi 3 squared. Let's try this. So we're going to have 1,300 times 2 pi 3 squared. And I'm getting 22.989. And boom, that's actually the answer for the average shearing stress.